Hi, in this video we will show that projections are linear transformations, and in some examples we will find the standard matrix of projections as linear transformation. Let me start with recalling what was projection on a vector. So projection on a vector, projection on vector u in Rn is given by this. So projection on u, this is the notation. When we apply it on a vector v, this is u dot v over u dot u, then scalar multiplied to u. Well, the fact or proposition here is that projections are linear transformations. Meaning what? Meaning that if we start with projection of u going from Rn to Rn, which sends every vector v to projection of v over vector u. This is linear, meaning that projection of c1 v1 plus c2 v2 over u is going to preserve the linear combination. Meaning that, well, let us start using the formula we have here. So instead of v, we have a c1 v1 plus c2 v2 over u dot u scalar multiplied to u. Now, here in the numerator, you notice that, well, this is dot product. Dot product works nicely with vector addition. It means that it distributes over vector addition. And then there's a scalar multiplication c1 here. That will come out. So it will be c1 dot u dot v1 plus c2 u dot v2 over u dot u. Then this as a scalar number multiplied to u. Now we can separate denominator and we will have c1 u dot v1 over u dot u. Then scalar multiplied to u plus c2 u dot v2 over u dot u scalar multiplied to u. This piece here, this is projection of vector v1 over u, then scalar multiplied c1 to that, and then this one here is projection of v2 over u scalar multiplied by c2. And this is what we were looking for. Projection of a linear combination is linear combination of the projections. Okay, so now that we know these are linear transformation, one can ask, well, for all linear transformation, we can find a matrix, a standard matrix. How about projections? Well, let's do this in some examples here. So projection on u here, then we have projection of on u of, well, let me write x, y, z. This is from R3, so the projection will act on vectors with three components. Then u1 negative 1 2 dot x y z over u dot u. Then scalar multiplied by u itself. This then gives us x minus y plus 2z, 1 plus negative 1 squared is 1 plus 2 squared is 4 times 1 and negative 1, 2. Well, this is a formula. You can make it simpler even, but let me just leave it there. To find standard matrix, we need to find projections or the linear transformation acting on the standard basis 1 0 0 0 1 0 and 0 0 1. So here if I plug in x1 y and z 0, then we will have 1 over 6 of 1 negative 1 2. In other words, 1 over 6 negative 1 over 6 and 1 over 3. Projection on u of E2, this is going to be negative 1. Y is 1, everything else is 0, or negative 1 over 6, 1 negative 1 2. This is going to be negative 1 over 6, 1 over 6, negative 1 over 3. And the last piece, projection on u of E3. This will be 2 over, let me just straight go ahead. This will be 2 over 6, which is 1 over 3. This will be 1 over 3, negative 1 over 3, 2 over 3. Then when you have these guys, the standard matrix of the projection over U is, what do we do? Put this guy in the first column, 1 over 6, negative 1 over 6, 1 over 3. This one in the second column, negative 1 over 6, 1 over 6, and negative 1 over 3. Oops, there's the third column. And third column goes there, 1 over 3, negative 1 over 3, 2 over 3, and that's it. That's what we wanted to find. How about projection in R2? Well, in R2 the computations are easier, but I will do very general vectors. So here I have vector u, which has 2 components. So projection over u of x, y, this is going to be u dot v. So it will be d1x plus d2y over d1 squared plus d2 squared, then d1 and d2. Now we need to find projection of E1 over U. This is x is 1, y is 0. So d1 squared plus d2 squared. And this is d1 and d2. Which gives us what? Which gives us d1 squared over d1 squared plus d2 squared, and d1 and d2 over d1 squared plus d2 squared. And projection of E2 on U is going to be d2, d1 squared plus d2 squared times d1, d2. This gives us the second column, which is d1 d2 over d1 squared plus d2 squared, d2 squared over d1 squared plus d2 squared. Then the matrix of transformation, the standard matrix, is, you can write d1 squared plus d2 squared, d1 and d2 d1 squared plus d2 squared, d1 d2 d1 squared plus d2 squared, and d2 squared over d1 squared plus d2 squared. Or, well, sometimes you can write this, factor out this d1 d2 squared, 1 over that, and write it as d1 squared d1 d2 d1 d2 d2 squared. So that's it. That forms a very good class of linear transformation that we studied here.